Today in this video, we're going to be looking at doing hypothesis testing or finding inferences about dependent samples. So we've talked about independent samples already when you've got two samples and you're comparing them, but of course they were independent. So today is, well, what do you do if they're dependent? This actually goes by a few different names. It's sometimes called the match pairs t-test, which really already tells you which test we're going to be using. It's also called the pairs t-test. It doesn't matter the name. You're comparing two sets of samples that are dependent on each other. And yes, we're going to be using the t-test. With dependent samples, there's got to be some sort of relationship whereby each value in one sample is paired or corresponded with a value in the other, which tells you you're going to have the same sample sizes. Whatever the sample size is of the first one, it's got to have a corresponding sample to the second one, because we're going to be finding differences. Well, if there's nothing there, there's nothing to find the difference of. So they've got to have the same sample size, and that'll hopefully be a little more clear what I'm saying there in just a second. Here's an example of what I mean by dependent. The paired t-test would be used to determine if there is a significant difference between pre and post treatment of blood pressures. So you're taking a person, that's what makes it partly dependent. It's the same thing. In this case, the thing is a person. You're taking the same person, you've got a treatment prior and a treatment afterwards, and you are comparing those. This can be used in the medical community with, say, a rare disease where you might not be able to find a lot of people to treat. So you've got to treat the same person before and afterwards, and somehow design your experiment to have measurements that you can actually compare. Okay, so dependent samples when we're comparing two sets of them. That's what this is about. There are some requirements. The sample data obviously has to come from dependent. It's got to be from the same thing. Samples still have to be simple random samples. That's pretty much every one of our hypothesis tests. Either or both of these conditions have to be satisfied. The numbers of pairs in the sample data is larger than n, is large. And what I mean by that is greater than 30. Or the pairs, so we're going to be pairing them up, have differences that are from a population that have a distribution that's approximately normal. So if you've got smaller, we are going to be using the t-test. So you can have smaller than 30, but you have to know that it's approximately normal. So I'm not going to go through the normality tests as I do this today. I'm just going to say, hey, these are normal, so we're going to go from up there. But if you're doing an actual hypothesis test, and you haven't checked it, you need to, of course, use your test for normality. This is an example here. We talked earlier about the freshman 15. Okay, so this guy gaining 15. You've got a before, you've got an after, and it's the same person, so obviously it would be dependent. Some notations here. We're going to have D as the difference. So we've got individual differences between samples. Again, you're going to be taking samples from one and another and finding the differences. You got to subtract. Mu sub d, that is the mean value of differences, d, for the population of all pairs of data. And we've got this one here. We've got d bar. The mean value of the differences, d, for a paired sample. S sub d, that's the standard deviation of differences, d, in a paired sample data. And of course, n is the number of pairs in the data. All right, let's take a look at an example here. Oh, you got to know this when we do these dependent ones. Your null is always, you don't have to think about this, it's always going to be that there is no difference in them. Okay, that's going to be the null. And of course, if you get to reject that, then you'd say, oh, well, yeah, there actually is a difference between them. Okay, so you'd have enough evidence to support that if you can go ahead and reject the null. So this will always be this right here. You're always going to have, of course, the equality, but the equality is that the difference is equal to 0. Okay, so let's take a look at this example here. We've got a guy. He is going to go take golf lessons. And so he's played a bunch of rounds ahead, and he kept track of his scores for each of those rounds. That's these right here. So 82, 92, and so on. This was some rounds that he played before he got golf lessons. Well, he wants to find out statistically, did it actually improve his game to take golf lessons? Okay, so then this is some scores from after. Now, if you've ever played golf, or this goes for just about any sport, you know that there's a ton of variation. What you get from day to day changes quite a bit. And so, like, okay, well, that one, the after is actually a higher score. If you know anything about golf, lower scores are better. But this one's a lower score, but of course, that one was a high day. That one's lower, that was kind of a higher day. And so on. So it's really tough to compare this because of the randomness involved. And so that's where this hypothesis test can be really handy here. Okay, so we're taking a look at 8 rounds, before and after. And what do you mean by paired? So it really doesn't matter which ones you pair, but every set of numbers has to have, every number, put it that way, has to have one that goes with it. Because we're going to be subtracting is what we're going to do here. And you might say, well, do I have to line up the highs or the lows or anything? No, you don't have to do that because in essence, we're not really averaging the differences, but we're kind of looking at the average distance. That's the idea here. And we're saying, hey, that the average difference, the mean difference is equal to 0. That's going to be your null hypothesis. Or excuse me, I said that right, equal to 0. So there is no difference. Okay, we do know it's dependent because it's the same person. And we're going to do this at a 95% confidence level. So our alpha is going to be 0.05. I'm going to use the p-value method. I will be using the calculator here. And I'm going to show you a little trick to do with the calculator. There's our null and alternative hypotheses. Again, that the mean difference is 0. And of course, the alternative is that it's not equal to 0. So you do have to go through the process of finding the differences. And again, it doesn't really matter which ones you line up. Sometimes you're going to get positive numbers. Sometimes you're going to get negative numbers. The idea here would be if I added all these up and averaged them, that I'd end up with 0. Okay. Now, we got to take the variation into effect. Now, I want to show you a trick here. So you're going to be using your calculator if you've got data. You're going to want to go ahead and enter your data into list 1 and list 2. And of course, this is on the Texas Instruments. Now, if you arrow up here so that list 3 is dark like that, you can actually sort of write an equation of what you want it to do. Notice I know my stuff's in the way here, but I've got it going to list 2 minus list 1. So I'm actually going to have it do a subtraction for me. And so I go ahead and do that, and I hit enter, and there, and you'll see it's the same numbers I've got right here. So if you have, say you had 50 sets or 50 pairs, well, you can subtract one at a time, but it's really easy if you just use your calculator. You got to put your data in, but then you go to list 3 and just go, hey, list 2 minus list 1. It really doesn't even matter which one you subtract from which one. You're just going to do a subtraction. And it'll, of course, do all those subtractions. Okay, then what you're going to do next is you're going to go ahead and you're going to go to your t-test. Stats, test, t-test. And for this one, I'm going to be using data. And the data I'm going to have right here. I'm going to have that my mean 0. Okay, that's what we're going to put in there. That's going to be based off of this right here. Where's the data coming from? List 3. Make sure you adjust that. Put your list 3 in there. Now we got to base our tails off the alternative, so we're going to use the not equal for the alternative. And again, for this matched pairs, this needs to be 0 right there. Okay. Frequency, that should be a 1. Probably you don't have to mess with it, but if it's for some reason something else, make sure it's a 1. Then you go ahead, and I like to graph it out, and gives me my p-value right there, which you can see is 0.65, which is well above 0.05. And so in this case, I am going to fail to reject the null. Okay, so there's not sufficient evidence to warrant rejecting the null that the mean change is equal to 0. So what's the application then statement? The application statement would be that the golfing lessons for this guy just didn't seem to help. I'm not saying golf lessons don't help. I'm just saying they didn't seem to help this guy. And that's a matched pairs or a dependent sample. So it's dependent. You got to have two sets of data, two samples, and you're comparing them, checking to see if there's been a change. Matched pairs hypothesis test. Okay, I'm going to let you try one of these. So there's this idea out there that when it comes to the best actor and best actresses, so we're talking about the Oscars here. The Oscars, of course, are those awards that go to movies. There's a couple of big categories, the best actor category and the best actress category. And there's this thought out there that the best actor, it doesn't really matter how old they are. You got young ones, you got old ones, it doesn't really matter. But there's this thought that the best actress seems to go more towards the young ones. And what that would imply is that, you know, their looks are maybe taken into effect a little bit. And so that's what we're going to check here. This is actual data. And again, it doesn't really matter which ones you match up. But we've got best actors, we've got best actresses. Again, what you're going to have to do is find the differences, and it actually doesn't matter which direction you subtract. Do your t-test. The null is going to be that they are equal to 0, that the average mean is for the differences is equal to 0. The alternative is that they're not equal to 0. So why don't you go ahead and pause this, try that one, and see what you come up with. Okay, so here we go. Hopefully you got that in and you did the subtraction. You could do it manually too, but it's really nice to let the calculator do it. Again, the mean should have been 0, list 3. The alternative is not equal to 0, so that it's going to determine your tails there. And you should have got a p-value of 0.023, which if we're using 0.05, which we are right here, would say that we can reject the null. So the mean difference is not equal to 0, which means that there is a mean difference that's different than 0. So these are different. That implies that, yes, even though there's variation, they are different. So there is sufficient evidence to reject the null and support the claim that best actresses are younger than best actors. All right, if you want to play with these a little bit more, there's a few problems right there to practice with. Have a good day.